Chemical sedimentation definition. Chemical sedimentation refers to the process through which minerals precipitate out of a solution, forming solid sedimentary rocks through various chemical reactions. Unlike physical sedimentation, where particles settle out of suspension due to gravity or other physical forces, chemical sedimentation involves the transformation of dissolved substances into solid particles. This process typically occurs in environments where there is an abundance of dissolved minerals in water, such as in oceans, lakes, or hot springs. When conditions such as temperature, pressure, or chemical composition change, the solubility of certain minerals decreases, leading to their precipitation. This precipitation can occur through various chemical reactions, including precipitation reactions, ion exchange, or evaporation. One common example of chemical sedimentation is the formation of limestone. In marine environments, calcium carbonate dissolved in seawater can precipitate out of solution when the water becomes oversaturated with calcium and carbonate ions. This can happen due to factors such as the influx of calcium-rich groundwater, changes in temperature or pressure, or the activity of marine organisms like corals and shellfish that extract calcium carbonate from the water to build their skeletons and shells. Another example is the formation of evaporite deposits, such as rock salt, halite, and gypsum. In arid regions where water evaporates quickly, the concentration of dissolved salts in water bodies can increase to the point where they precipitate out as solid minerals. Over time, these minerals accumulate and form thick layers of sedimentary rock. Chemical sedimentation plays a crucial role in the formation of many economically important mineral deposits, including deposits of metals like iron, copper, and uranium. These deposits often form through processes such as hydrothermal circulation, where hot, mineral-rich fluids migrate through fractures in the Earth's crust and deposit minerals as they cool and react with surrounding rocks. Overall, chemical sedimentation is a fundamental process in the Earth's geology, responsible for the formation of a wide variety of sedimentary rocks and mineral deposits. By understanding the mechanisms and conditions under which chemical sedimentation occurs, geologists can interpret past environmental conditions and reconstruct Earth's history. Formation of chemical sedimentation. The formation of chemical sedimentation involves a complex interplay of geological, chemical, and environmental factors that contribute to the precipitation and accumulation of minerals in sedimentary rocks. This process can occur in a variety of environments, each characterized by unique conditions that influence the types of minerals formed and the sedimentary structures produced. Marine environments. In oceans and seas, chemical sedimentation is often driven by the interaction of seawater with the Earth's crust and marine organisms. For example, the formation of carbonate sediments like limestone begins with the accumulation of skeletal remains of marine organisms such as corals, foraminifera, and shellfish. These organisms extract calcium carbonate, CaCO3, from seawater to build their shells and skeletons. Over time, these calcareous remains accumulate on the seafloor and undergo compaction and cementation, forming limestone deposits. Evaporite environments. In arid or semi-arid regions with restricted water circulation and high rates of evaporation, evaporite deposits form through the precipitation of dissolved minerals from saline water bodies. As water evaporates, the concentration of dissolved ions increases until they reach a point of saturation, causing minerals like halite, rock salt, gypsum, and anhydrite to precipitate out of solution. Evaporite deposits often occur in closed basins such as playas, salt flats, and sabkhas, where the evaporation rate exceeds the inflow of fresh water. Hydrothermal systems. Chemical sedimentation also occurs in hydrothermal environments, where hot, mineral-rich fluids circulate through fractures and faults in the Earth's crust. As these hydrothermal fluids interact with the surrounding rocks, they undergo cooling and chemical reactions, leading to the precipitation of various minerals. Hydrothermal sedimentary deposits include ore bodies containing valuable metals such as gold, silver, copper, and lead, as well as minerals like barite, fluorite, and sphalerite. Groundwater systems. Groundwater can also play a significant role in chemical sedimentation, particularly in terrestrial environments. As groundwater percolates through rocks and sediments, it can dissolve minerals from the surrounding materials and transport them to new locations. Subsequent changes in temperature, pressure, or chemical composition can cause these dissolved minerals to precipitate, forming sedimentary deposits within fractures, caves, or pore spaces in rocks. Examples include travertine deposits formed by the precipitation of calcium carbonate from groundwater in caves and hot springs. Anthropogenic influence. Human activities can also contribute to chemical sedimentation through processes such as mining, industrial pollution, and the discharge of wastewater. Mining activities, for instance, can lead to the release of acidic mine drainage, which can dissolve minerals from rocks and sediments and deposit them downstream as sedimentary precipitates. Similarly, industrial effluents containing heavy metals and other contaminants can result in the formation of sedimentary deposits in aquatic environments. Overall, the formation of chemical sedimentation is influenced by a combination of geological, hydrological, chemical, and biological processes operating over various spatial and temporal scales. By studying these processes and the resulting sedimentary rocks, geoscientists can gain insights into past environmental conditions, geological history, and the distribution of mineral resources. Process of chemical sedimentation. The process of chemical sedimentation is multifaceted and involves a series of intricate steps that culminate in the precipitation and accumulation of minerals to form sedimentary rocks. This process occurs over geological timescales and is influenced by a variety of factors, including environmental conditions, chemical interactions, and the presence of organic matter. Below is a detailed exploration of the process of chemical sedimentation. Source of dissolved materials. Chemical sedimentation begins with the presence of dissolved materials in a solution, typically water. These materials may originate from various sources, including weathering and erosion of rocks, volcanic activity, hydrothermal fluids, or biological processes. The dissolved substances in the solution may include ions such as calcium, magnesium, sulfate, carbonate, and silica, among others. Saturation and precipitation. As environmental conditions change, such as temperature, pressure, or chemical composition, the solubility of certain minerals in the solution may decrease. When the concentration of dissolved minerals exceeds the saturation point, precipitation occurs. This process involves the formation of solid mineral particles from the dissolved ions in the solution. The precipitated minerals may include carbonates, sulfates, halides, oxides, and silicates, depending on the specific geochemical conditions. Chemical reactions. The precipitation of minerals during chemical sedimentation often involves complex chemical reactions. These reactions may include ion exchange, redox reactions, hydrolysis, and complexation, among others. For example, the formation of carbonate minerals like calcite or aragonite involves the reaction between calcium ions and carbonate ions in the solution to form insoluble calcium carbonate precipitates. Nucleation and crystal growth. Once the initial solid particles form through precipitation, they serve as nuclei for further crystal growth. Additional ions from the solution are attracted to the existing nuclei, leading to the growth of crystal structures. The rate and extent of crystal growth depend on factors such as temperature, pressure, ion concentration, and the presence of impurities. Under favorable conditions, crystals may grow to significant sizes over time. Aggregation and sedimentation. As mineral particles continue to grow, they may aggregate together to form larger clumps or aggregates. These aggregates gradually settle out of the solution under the influence of gravity, a process known as sedimentation. The rate of sedimentation depends on factors such as particle size, density, shape, and the viscosity of the surrounding fluid. Fine-grained particles may settle more slowly than coarser particles due to their smaller size and increased surface area. Diagenesis and lithification. Once sedimentation is complete, the accumulated sediment undergoes diagenesis, a series of physical and chemical changes that transform loose sediment into solid rock. Diagenetic processes may include compaction, cementation, recrystallization, and mineral alteration. Over time, the sedimentary deposits become lithified into sedimentary rocks such as limestone, sandstone, shale, and evaporites through the consolidation of mineral grains and the binding of particles by cementing agents such as calcite, silica, or iron oxides. Burial and geological processes. Finally, geological processes such as tectonic movements, uplift, and erosion may bury, deform, or expose sedimentary rocks over millions of years. These processes contribute to the geological cycle, where sedimentary rocks are continuously formed, modified, and recycled through Earth's dynamic processes. In summary, the process of chemical sedimentation involves the precipitation, aggregation, and lithification of minerals from solution to form sedimentary rocks, representing a vital aspect of Earth's geological history and the cycling of materials within the Earth system.